So lesson number 2 looked at what P and Q does to the graph of my quadratic. P moves it left or right, Q moves it up or down. What we're going to look at today, as soon as the computer turns back on, is what A does to the graph. What effect does A have on the graph? So if we have this graph here, x minus 2 squared, so it's my quadratic that's been moved 2 units to the right. If I had 2 times f of x, 2 times f of x means that I have 2, and where I see f of x, I substitute in x minus 2 squared. So if I put that in my graphing calculator, I'm going to start by changing the window settings. It went from -5 to +5, and then my y's went from -1 to +11. So my graph would be 2 times x minus 2 squared. And I have my x squared, or sorry, it shouldn't be x squared, it should be x minus 2 graph. Delete. There we go. X minus 2 squared. So the first graph is my transformed graph, and my second graph was the original. So this was my x minus 2 graph, and this is my 2 times x minus 2 squared graph. It makes it skinnier. So if I did a quick sketch of what this looked like, it made the graph skinnier. That was my 2 times x minus 2 squared. My colors to match up here. Then if I take a 1/2 and graph that one, so instead of putting 1/2, I'm just going to put 0.5. X minus 2 squared, so that'll be the third graph that gets drawn. That graph ended up being fatter. It went to the outside. Now again, be honest, how many of you think this seems completely backwards? The 1/2 made it bigger and the 2 made it smaller. Okay. It does seem backwards. Okay. This 2 here, would you say that it's with the x or with the y? It's with the y, because if it was with the x, it would be inside the brackets, would it not? So if I wanted to move this over to the y, how would I do that? Divide by 2. Now does it make sense why it's skinnier? Same thing on this side. How do I get rid of 1/2? Times it by 2. Makes sense that it's fatter now? So if I go back to my graphing calculator and I look at my table of values, y2 is my original graph. If I look at the y1, which was my 2x, my y values double, which actually brings them up. So my y values, back to the graph here. The y value that was at 1 in my green graph is actually at 2. It's twice as high. My y value that was at 4 is now at 8. It's twice as high. So it's like I stood right here on the vertex and I grabbed this graph and I pulled it up. And when I pulled it up, it caused it to get skinnier. Whereas with this one, this was my 1/2, my y values are half the amount that they were. So a y value of 1 now became 1/2. The y value that was at 2 is now at 1. The y value that was at 4 should actually be at 2, but I don't have it drawn to scale. But in that case, with the 1/2, it's like it got pushed down. And when I stood on this part and I pushed these two anchors down, it caused the graph to bowl out. So, compared to the graph of f of x, when I put the number 2 into the graph and I get 2 times f of x, what I get, I want you to cross this out, is we get a vertical stretch. We do not use the word expand and compress. It's a vertical stretch. And it stretched it by a factor of 2. Those y values were twice the amount that they were before. My 1 became 2, my 2 became 4, my 4 became 8. So it was stretched by that factor of 2. The y-intercept of the graph is double the y-intercept of the original. So in this graph, the y-intercept was 4. In my green graph, it's 8. When I go to 1/2, again, we do not use the word expansion and compression. We say it's a stretch by a factor this time of 1/2. Again, because my y values are half the value they were before. And so the y-intercept of the new graph is half of the original. Things to note are these two. The general name given is a stretch. Don't worry about the word expand or compress. Okay? We don't use the word expand and compress simply because a vertical expansion can look like a horizontal compression and it's really confusing. So we just say it's a vertical stretch. It's a vertical stretch by a factor of 2. It's a vertical stretch by a factor of 1/2. The vertical stretch is anchored by the x-axis. What it means is your x-coordinates stay the same. It's your y-coordinates that moved. So in this case, I stand on that point that's on the x-axis and I pull everything from there. So I pull it up by a factor of 2. That's stretching all of my y-coordinates. It does not stretch my x-coordinates. So the effect of the parameter of A is that it results in a vertical stretch. And it's a vertical stretch by a factor of A. And F I'm not going to worry about. What happens if I make this negative now? So this is my equation, y equals x squared. If I wanted y equals negative f of x, I would have negative x squared. So the question I have for you, is the negative with the x or with the y? So if the x, if the x was negative, what is negative x squared equal to? Positive x squared. Is that the same as what I have here? No. So is the negative attached to the x? No, it's actually attached to the y's. So what's happening here? My y values are becoming the negative. So imagine, before we graph this, if my y values become the negative of what they were, where's this graph going to go? It's going to go down. Let's check. So start off by changing your window settings. This time my y's are going to start at -9 and go up to +9. So I'm going to graph x squared first. So that's going to be the graph that's going to go up. And then if I put in -x squared, we're predicting that that graph's going to go down. Oh, there it goes. So it's the exact same shape as this graph is right here. It's just opening down. And then if I have -2f of x, I get a -2x squared. So what does the 2 do to the graph again? It makes it skinnier. It's that vertical stretch by a factor of 2. So my y values are going to become twice of what they were. So the 1 will become 2. A y value that's at 4 will become 8. So 1 becomes 2. My 4 becomes 8. And this ends up being that y equals -2x squared. So if I look at my first graph, the one that I did in blue, that was my y equals -x squared. Where's the vertex of that graph? Zero and 0. Do I have a minimum value or a maximum value? Maximum. Now I have maximums. So max of 0, axis of symmetry would be x equals 0. How do I describe this? What did I do to this graph from the black to the blue? I reflected it. It is a reflection in which axis? Which axis did I reflect it over? So it's a reflection in the x-axis. That's the description of the transformation. So now if I look at the green graph, which was y equals -2x squared, the vertex is still 0 and 0. It still has a max of 0 and an axis of symmetry where x is equal to 0. That hasn't moved. I still have a reflection in the x-axis. And what did that 2 do to the graph? Yep. So vertical stretch by a factor of 2. Not a -2. My stretch factor is just, it's always positive, or it doesn't even really have a sign. That negative is taken care of with the reflection. So the stretch factor is what did I pull those down by? I multiplied them all by 2. Not by a -2 because I had already done the negative when I flipped it over. So as I was saying before, it's a vertical stretch by a factor of A about the x-axis because my x-axis is the anchor point. That's what I'm anchoring the graph to. This part right here gives us kind of a summary of what A, P, and Q do to the graph of y equals x squared. A indicates a vertical stretch. Don't worry about these two lines, about the compression and the expansion. A just tells me that there's a vertical stretch about the x-axis by a factor of A. When A is less than 0, I have a reflection. P tells me I have a horizontal translation. When P is greater than 0, the parabola moves to the right. That means I have y equals x minus p squared. When it's negative, I have x minus negative p squared, which looks like an x plus p squared. Q indicates a vertical translation. When Q is greater than 0, it moves up. So the way that that looks on the graph is y equals x squared plus q. When q is less than 0, it moves down because it would be x squared minus q. P and q represents the coordinates of the vertex. X is the equation of the axis of symmetry. The other thing that you could write here to add to your notes is when A is less than 0, the graph opens down. And when it is greater than 0, the graph opens up. So if I have the function f of x equals 2 times x plus 4 squared minus 3, compared to this graph right here, what did we do to this graph to get to this point? So start with the 2. What did the 2 tell me to do? It divides the y by half, or sorry, it multiplies. It makes it look skinnier, but it's still multiplying it by 2. It's the factor of A. So I have vertical stretch, factor of 2, and that was about the x-axis. And then I went, what does the 4 and the 3 tell me? Okay, so 4 left, 3 down. So Marika and Curtis look at this, and they discuss how I could sketch the graph without using the graphing calculator. So Marika says, I'm going to stretch it first, and then I'm going to translate it. Curtis is going to translate it, and then he's going to stretch it. So we're going to do each of them separately. So Marika stretches first. It's a stretch by a factor of 2. Which means these points here all get doubled. So if y is 0 and I double it, it still stays at 0. When y is equal to 1, it becomes 2. When this y value right here is 4, it's going to become 8. So this is what Marika's graph looks like after her stretch by a factor of 2. So the dotted line was after the stretch. Now, if she takes those points and moves them 4 units to the left and 3 units down, 2, 4, 3 down, this point right here moves 4 to the left and 3 down. This point is going to move 4 to the left and 3 down. This point at 8, so it's at positive and negative 2 and 8, moves 4 to the left, 2, 4, and 3 down, 4 to the left, and 3 down. So Marika's final graph is right here. Curtis does the opposite. Curtis translates first. So if he takes this graph and moves it 4 to the right, or sorry, 4 to the left and 3 units down, his point of 0 and 0 becomes -4 and -3. These 2 points that are at 1, 4 and -3, 4 and -3, now actually become -3 and -2 and -5 and -2. And then my last points, which were at 2 and 4, if I move 4 to the left and 3 down, we're at y is equal to 1 and x is equal to -2 and -6. So this is Curtis's initial graph. So that is Curtis's after the translation. Then he stretches it by a factor of 2. So it's the y values that become stretched. So my y value that's at -3, if I multiply it by a factor of 2, becomes 3 times 2. So it becomes -6. This y value that is at -2 would become -4. This y value that is at +1 would become +2. Maybe I'll do those in a different color just so that it shows up better. So these are the points that Curtis obtains when he does the stretch, because the y values get stretched by a factor of 2. So in this case, Marika and Curtis do not get the same graph. So the calculator is going to settle the argument. So my graph, my original graph was x squared. My new graph is 2 bracket x plus 3 bracket squared minus 4. And we'll put this on a standard grid. Whose graph did I get, Marika's or Curtis's? Look at where the vertex is. So does the vertex look like it's at, so Marika's vertex was at -4 and 3. Do I have I think I have the equation written wrong. Yep. Be x plus 4, sorry. X plus 4 minus 3. That might be better. So does my vertex look like it's at Marika's, which is at -4 and -3, or Curtis's, which is at -4 and -6? Probably Marika's. If I couldn't determine it, if I was looking at it and I wasn't absolutely sure, to find the vertex, second calc, you're finding the minimum point. So when you press 3, it gives you left bound. Means it wants to be on the left side. Now right now, I'm on the y1. I'm on this graph. if I go down, I jump to my next graph. And then I just have to scroll over. So the left bound means on the left side of the minimum point. Enter. Right bound means I need to move to the right side of the minimum point. And again, I look to make sure that the arrows are pointing at each other. Press enter again. And depending on the way that the screen is, it gives me negative 3.989999, which is negative 4, and negative 3. So whose graph do I have, Marika's or Curtis's? Marika's. So does the order in which I do these transformations matter? Yeah. You have to stretch first. You can remember this two different ways. Stretching and reflecting, we're multiplying things. To do a stretch, we were multiplying by a factor of A. To do a reflection, it's like multiplying by a negative 1. Multiplication comes before addition and subtraction. Order of operations, all over again. So you can remember it that way, or you can sort it out. S-O-R-T, the O is just there for decoration, or actually for the word or, because I can stretch or reflect, and then I translate. The other analogy I have, a sport analogy. When you guys are getting ready to play volleyball or basketball, the first thing that you do is you stretch, you do your warm-up first. Then usually you have your powwow, your reflection, you're trying to figure out what you're going to do. Then you move into the game. So you stretch, you reflect, and then you translate. Okay? So yesterday we were looking at analyzing the quadratic functions. We looked at the general equation y equals a times x minus p squared plus q. P and q cause the graph to shift left and right and then up and down. And A causes the graph to either open up or down, and it affects whether or not it has a fat opening or a skinny opening. The last thing that we looked at was the order in which we would apply these transformations. So I introduced the acronym of sort it out. So stretches and reflections can be done first, and the other way to remember that is the stretch and the reflection. A stretch is multiplying by a factor of 2, a factor of 1/2. A reflection, in a sense, is almost like stretching it in the negative direction. So it's multiplying it by a negative. Well, multiplication happens before addition and subtraction, and that's what you're doing when you're translating. You're adding it, moving it to the left or the right, up or down. So you can remember sort, you can remember order of operations, but the translations are always done at the end, unless the question specifically says, do it in this order. But otherwise, the implication is that you would stretch first, reflect, or reflect and stretch, but the translation would happen at the end. So if we look at class example number 2, again, we're asked to describe what has happened to this graph of y equals x squared to get to the new equations. So what have I done to y equals x squared to get to the equation of y equals negative 1/4? So what does the 1/4 tell me to do? So in terms of my equation, which one of the letters does 1/4 belong to? A. So in this question, A would be equal to, I can look at it, I can split it up into a 1/4 and a negative 1. A is my stretch and my reflection factor. So if A is equal to 1/4, that becomes a vertical stretch factor of 1/4. And then I can put in about the y-axis, or about the x-axis. The negative 1 is my reflection. And the reflection is in the x-axis. So we stretch about the x-axis and we reflect in the x-axis. Now, on a test for me, if you put a reflection in the x-axis, or sorry, if you put a stretch in the x-axis, I'm not going to mark it wrong. For a multiple choice test, because transformations happens next year as well, I'm not going to give you a statement where it says vertical stretch by a factor of 1/4 in the x-axis and a factor of 1/4 about the x-axis, because that is a very minor part. What we're more concerned about is that it's a vertical stretch, the factor is 1/4, and then it's anchored to the x-axis. That's what this about the x-axis means. So if I look at B, what should I do to start off with?
Subtract the 1/3 from like y and
Do I subtract it?
you times it.
I times it. So what is my A value? 3. So if A is equal to 3, what kind of a transformation do I have?
Vertical stretch factor, or vertical stretch by factor of 3.
I guess I should put vertical stretch first, not factor. So vertical stretch factor 3. Okay. What about that 6? What letter does it correspond to? P. So is P equal to 6 or is P equal to -6? -6. So when P is equal to -6, what does that tell me to do to the graph? 6 units to the left. If you look at the equation, the P is put with the x, which means it affects the x coordinates, so it's a left-right movement. That -6 means I go to the negative. Always remembering that in my original equation, it's always written as an x minus P. Okay, class example number 3. The following 3 transformations are applied in this order to the graph of y equals x squared. A reflection in the x-axis, a vertical stretch by a factor of 1/3 about the x-axis, and a translation of 7 units to the right. At the end of the 3 transformations, the point 1 and t is on the resulting graph. Find the equation of the image. So let's start off with the equation. My original equation is y equals x squared. If it undergoes a reflection in the x-axis, what letter am I impacting? A, P, or Q? Reflection. It's the A value. Because a reflection, think of it as a negative stretch. So my A value would become a -1. So my new equation would be y equals -x squared. Then I have a vertical stretch by a factor of 1/3. So which letter again am I impacting?
Is that also?
That's also A again. So what would I replace A with? 1/3. So my new equation would be y equals -1/3 x squared. And then the last thing that I do is I go translation of 7 units to the right. So what letter takes care of translations left and right?
X.
The x, which is which letter in my general equation? P. So, oops. And if I'm going 7 units to the right, would P be equal to a +7 or a -7? It would still be, I know what you're saying. I know what you're meaning, or at least I hope. Because you are looking at it as that. but it's always written like this anyways. So when I ask if P is positive or negative, P would have to be positive, because if it was negative, I'd get minus a negative 7. Okay? So this is my final equation. This is the equation of the graph that is reflected and stretched by a factor of 1/3 and translated 7 units to the left. So now it says state the coordinates of the vertex of the final graph, of the vertex. So the vertex of the original graph is what? Y equals x squared looks like this. So where does the vertex go through? 0 and 0. So I start off with 0 and 0. If I multiply my y value by a negative 1, I still get 0 and 0. If I stretch that value by 1/3, what will I get? So stretching means multiplying. So if I multiply this by 1/3, I'm still going to be at 0. So on this point, the stretch and the reflection does not move that point. Finally, I then move it 7 units to the right. So if I move this point, so the reflection would have caused the graph to open downwards. The 1/3 would have caused it to get fatter. And then I move it 7 units to the right, which is going to shift it that way. So then where would my vertex end up? 7 and 0. So then the last part says find the value of t, my point 1 and t. So if I have the point 1 and t, it means if x equals 1, what would be the value of the equation? So I substitute 1 into this equation. So 1 minus 7 is and negative 6 squared. So I'll get negative 1/3 times 36, which would equal negative 12. So the point would be 1 and negative 12. So class example number 4 asks us to complete the following table. So again, we're looking at this being my standard equation. This is what the equation normally looks like. So it goes back to what does A tell me to do and what do P and Q tell me to do. So in this equation, I have negative x plus 3 squared minus 4. So if I had to rewrite this equation as an x minus P, it would be x minus what? Negative 3. The vertex of the graph I find with my values of P and Q. So the value of P and Q is the vertex, which in this case would be negative 3 and negative 4. The min and the max value, the value itself is the y-coordinate of my vertex. So I know the value is a negative 4. Whether it is a min or a max depends on whether the graph opens up or down. What tells me whether the graph opens up or down? The negative on the A. So is there a negative A value? So this opens down, which means it's going to have a maximum value. Because this opened down. The axis of symmetry, it's an equation that's an x equals, and it equals the vertex. the x-coordinate of the vertex. So with these two, or with this information, what I can tell you is that if I had to sketch this graph, I'll sketch it right here, my vertex would be at -3 and -4, and the graph would open down. That's general, or what my first initial sketch would look like. I could figure out the y-intercept by letting this be equal to 0. So I have 3 squared, which is 9, times -1, so I'd have a -9. It would go through at -13. So I could add that information to the graph. And I could sketch that portion of it. If this graph opens down and looks like this, does it have any zeros to the equation? How do I know it doesn't have any zeros? What is it missing? How do the zeros connect to the graph?
Oh, it doesn't intersect the x-axis.
It doesn't have any x-intercepts. So without any x-intercepts, there's no zeros, which means there's no roots. So I can't solve that equation. The domain, all parabolas that open up and down have the same domain, and that is that x could be anything. Because this parabola is just going to keep getting fatter and fatter and taking up more of the x-axis. And it doesn't matter if it opened up or down, it's still going to do the same thing. So the domain, I can say that x can be anything, or I could write it as -infinity to +infinity. The range is connected to the vertex, because the vertex being right here at -4, from there it tells me the values either have to be greater than -4 or less than -4. That's the limitations with my range. Depending on that graph opening up or down, I'm never going to have a situation where all possible. So if we look at the last, or the next equation, where would my vertex be? Zero is correct. Is it a -9 or a +9? +9. This equation is given to you on a formula sheet, so you won't have to memorize the equation. You just have to keep looking back. It always has to be written as an x minus. So if it's written as an x minus, whatever the p-value is becomes that vertex. Okay? Does this have a min or a max? A min, because this opens up. And what is the minimum value? The axis of symmetry.
X equals 1.
The domain. Any real number. And the range.
Y is greater than or equal to 0.
One thing I should point out, if you're using set notation for your domain, you would use set notation for your range. You would not have a situation where I'd write the domain like this, and then I'd write the range like that. You use a consistent form. So if I'm going to use interval notation, I would go -infinity to +infinity for the domain, and then 0 to +infinity for the range. I maintain the same style. It's kind of like changing fonts in the middle of writing an essay. You wouldn't change the font of your essay from Times to like Chiller in the middle of the essay because it just wouldn't flow. It's the only one I could think of. Okay, your questions that I want you to work on. Question number 1, parts C and D. Question number 2, parts A and B. Question number 6A. 7A and C. and then the multiple choice and the numerical response. So question number 9 and 10 this time.